Today we're going to be working on an absolute classic in the world of first year physics. It's projectile motion. Going into a problem like this, you should be a little bit familiar with the kinematic equations and the variables that are in those equations, so words like accelerations, velocities, displacements, and time. And you should also be a little bit familiar with vectors, words like vector components and magnitude of a vector and things like that. Okay, so that being said, let's get into it. Pause the video, give this question a read. Okay, so every projectile motion problem that you're going to see involves some object flying through the air. So in this particular problem, we've got our phone being hurled off of a cliff. It's going to follow that characteristic parabolic trajectory. Okay, I want you to think of the motion of the phone. Instead of thinking of this parabolic arc, think of the phone as having two different types of motion that are happening simultaneously. Okay, we've got horizontal motion, x direction motion, and we've got vertical motion, y direction motion. And both of these types of motion can be treated independently. That's one of the keys to dealing with two-dimensional problems like this. Okay, so that brings us to our first step to tackle this problem. It's going to be getting organized, okay? And that involves doing a couple things. One, we want to define our positive directions, right? So all of the variables, with the exception of time, in the kinematic equations are vectors. So their direction matters, right? And how we define the direction of a one-dimensional vector is just with either a positive sign or a negative sign. So it's important that we decide early on which directions we're saying are positive, and we be consistent with that. Okay. Next thing we want to do is break all of our givens into x stuff and y stuff. Okay. And by givens, I don't just mean things that are said explicitly in the problem. I also mean implicit givens that we can sort of tease out of the context. Okay. So let's just go through systematically the variables in the kinematic equations and write down what we know about each of them. Okay. So right away we can see that we know something about the initial velocity of the phone. In fact, we can write down both its x and its y components. Okay, so the x component of that initial velocity, right, that 15 meters per second at a 40-degree angle, that's going to be 15 cosine 40 degrees. Plugging that into your calculator, you should get 11.5 meters per second. And similarly, we can do the same thing with the y direction. The y component will be 15 sine 40 degrees. Okay. And plugging that into your calculator, you should get 9.64 meters per second. Okay. What other variables do we have in the kinematic equations? Well, we have acceleration, right? The rate of change of velocity. Okay, so can we say anything about the x or y accelerations of this phone? Well, we know conceptually, right, at least in the absence of air resistance, there's not going to be any forces that are acting on this phone in the left or right direction while it's flying. Okay, and if there are no x forces, there are no x accelerations, right? This is always going to be true of projectile motion. We have no x acceleration. Our x velocity is constant. Okay. But our y velocity is, of course, not constant, right? Gravity accelerates objects towards the surface of the Earth at a rate of 9.8 meters per second. Okay, we call that rate g. Okay, so our y acceleration is going to be negative g, negative meaning down, right? So negative 9.8 meters per second squared. Okay. What else? We have displacements, right? We don't know anything about how far the phone will be from the cliff when it hits the ground horizontally, but we do know the vertical displacement, right? When it hits the ground, that phone is going to be 20 meters vertically below where it started, right? So there's a delta y of negative 20, okay? We can even say something about the final velocity of the phone already without doing any math, right? Because we know if the x acceleration is 0, then the final velocity of the phone in the x is just going to be the same as the initial, right? It will still be 11.5 meters per second, okay? And of course, we don't quite know the final velocity in the y direction. If we did, there wouldn't be much of a problem. Okay. Lastly, we've got time. We don't know anything about that just yet. We don't know how long the phone is in the air, and that's fine. Okay, so to move on to the next step, you want to be on the lookout for 3 pieces of information in one direction. As soon as we've got 3 values in either the x or the y, we can go ahead and solve a kinematic equation in that direction. Okay, so if you notice in the y direction here, we know 3 things. We know the initial y velocity, we know the y acceleration, and we know the y displacement. So that's enough to move on to step 2, which is to pick a kinematic equation and solve. Okay. So this is a point where we can be a little bit strategic, right? If you notice that each of the kinematic equations is missing one variable. So in particular, there's one that is missing time. And that's useful to us because we don't know how long the phone is in the air, and we don't particularly care about it either. So we might as well just neglect it from the problem if we can. And we can do that by picking this kinematic equation to work with. Okay. So you'll notice that we have values, we have numbers for every variable in this equation except for the final y velocity. So we can just plug in and solve. Okay, so v naught y, it's going to be 9.64. We'll square that. And then we have 2 times negative 9.8, and then times negative 20. Okay, plugging all that into your calculator, you should get that Vy squared is 485. Okay, taking the square root of both sides, we get that Vy equals 22 meters per second. Okay. You may be asking yourself, hang on, I thought we defined the positive direction to be up. So why did this final velocity come out positive? We know that the phone should be going down and to the right. Okay. And there's a bit of a subtlety here. Right? Remember that when you take the square root of a number, there's actually 2 solutions that can satisfy this equation. So this is technically plus or minus 22 meters per second. So we have to be thinking to take the negative solution here. Okay, so our final y velocity is actually 22 meters per second in the negative direction. Okay. So now that we have both the x and y components of our final velocity, it's just going to be a matter of combining them as in a triangle to get the magnitude of that final velocity. So that's going to be our third and final step. It's some vector stuff, right? We want to build the triangle here. Okay. So again, we have the components of that final velocity. Okay, so the x component is positive 11.5 meters per second. Our y component is negative, so in the down direction, so Vy 22 meters per second down. And this resultant vector, this is what we're after, right? We need not just its length, its magnitude, but we also need its direction, the angle that it makes with the x-axis, theta. Okay. So we can find the magnitude of that final velocity just using Pythagoras, right? A squared plus b squared equals c squared. Okay. So plugging that all in, you should get a final velocity of 24.8 meters per second. Round that to 2 sig figs, 25 meters per second. And then finally, we need our angle theta. We can get that by using any of the 3 trig functions, sine, cos, or tan. I'll use tan, sort of a convention. Okay, so tan is opposite over adjacent. So theta is going to be the inverse tan of Vy over Vx. Okay, and that will give us 65 degrees. Okay, one last little asterisk here. 65 degrees is technically not a direction, right? We need to say 65 degrees relative to something. So in this case, we might say 65 degrees below the x-axis. And that's a complete answer. Okay, so there you go, projectile motion.